Good afternoon, this is Schweitzer. We're going to talk about the mathematics of a solid, the composition of a solid. Now, a couple things you might want to note here is that we're just going to walk through like one example, maybe two. For you to become proficient at this, you really need to try your own. Most of the stuff we have in our workbook has the answers. So try it, work it through, try a problem, and gain your proficiency in that manner. So how do we express the composition of a solid? One of the main ways we do it is called percent by mass. And this is going to be percent mass equals the mass of whatever you're looking at analyzing divided by the total mass times 100. We do this a lot, let's say, in the human body. You could say, what's your percent mass of body fat? Alright, so that would be body fat. That would be the mass, total mass of fat in your body. And fat, of course, is critical to quality and comfortable functioning of your body. So having fat is required. Mass of fat divided by the total mass. Definitely times 100 percentage. Not too much, but some. Okay, so let's try this in terms of something that is obviously the best candy bar that a person could ever want, which is the Snickers bar. So what is the Snickers bar? Total mass of a Snickers bar is 57 grams, and the total sugar as listed on the package is 27 grams. Could you estimate the bar to be more or less than 50%? Well, 27, is that half of that? 27 plus 27 would be 54, so it's slightly less than 50%. It's not quite half of the total. Let's look at the actual percentage. Okay, so let's try this out. We have the case mass of 27 divided by 57 times 100. Grab your calculator and you'll get your percent mass. Alright, so the percent mass is 27 divided by 57. So it's about 47.3% sugar. 47.3% sugar. Now, what does that mean, 47.3%? That's a fictional number. And what I mean by fictional, it means out of a pretend 100-gram Snickers bar, which would probably be pretty close to a king-size bar. So if you had 100 grams of Snickers, you would have 47.3 grams of sugar. If you had a 1,000-gram Snickers bar, which would be awesome, by the way, you would have 473 grams of sugar. That's a lot of sugar. Now, next question is, what would be the mass of sugar in 6 Snickers bars? We're trying to get you to an idea here to understand that the sample size, as I've kind of gone through here, sample size, okay, does not matter. Sample size can be any mass. If you had 1 pound of Snickers bars, if you had 1 ton of Snickers bars, what would be the amount of sugar? 43% of that. Now, calculating out the actual mass of sugar would be another option here. Let's take a moment and do that. I'm going to wait for that for 1 second here. And here we go. So what is if you had, well, we know it's easy if you have 100 grams of Snickers bars. All right. But how would you do it if you have, let's say, 350 grams of Snickers bars? Okay, so this is important. Okay, so my ratio here, you can use a simple linear relationship, linear ratio, if you would like. And sometimes we fall back onto that. Okay, it's 47.3 grams out of 100 equals grams to Snickers bars. This is the total mass. Okay, so if I have 350 total, simply cross multiply and divide, cross multiply and divide, and you get your answer. Let's do that quickly so you can check your math. 350 divided by, times 47.3 divided by 100 equals 165 grams. Now, most people wouldn't do that, this whole thing. They would just say 47, they've been trained at 47.3%. What you do is just convert this to a decimal, 0.473, multiply it times 350, and you get your same answer. So keep in mind, this is a little bit of math that we're going to be using a lot of as we go forwards. Okay, so next one. Percent mass is consistent with all sample sizes, so it is not. So the sample size does not matter. What is the percent mass of carbon in a Snickers bar? Okay, so in actual sugar. So the sugar we're using in the Snickers bar is sucrose. So let's look a little closer. Now again, what we did so far in this thing, well, we took our Snickers bar and it's got a certain amount of sugar in this thing. And we did the percent mass of the sugar for the entire bar. Now we're going to take a little speck of sugar and let's analyze that dot. That dot is sucrose, C12H22O11. And at that point, okay, what's the percent mass of carbon in a sucrose molecule? Now again, the sample size doesn't matter. You could use 1 molecule, or you could use 10 grams, or you could use 1 mole. Okay, we just talked about that. And we're going to use a mole because on the periodic table, it is very convenient to look on there and see all the values on there. So we're going to get the mass of 1 mole, which is also called the molar mass, or the molecular weight. So it's going to be 12 times 12. This is going to be 22 times 1. And this is 16 times 11. And this is going to give you, if you have 1 mole, how much are you going to weigh? And of the weights, what is the contributing factor of these per each substance? And that's pretty important. So 12 times 12 is going to be 144. This is just 22. And 16 times 11 should just be 176. 176. Add them all together, and we get 342. So lots of kids can see this pretty easily, that the whole thing weighs 342. Therefore, how much of it is contributed by the carbon? Let's go back to our percent mass formula. Percent mass is the mass of X divided by the total, okay, times 100. Okay, so that's going to be 144 divided by 342 times 100 will give me my percent mass carbon. Is that half? It's going to be close. I'm guessing not, because 150 is half of 300, so not quite half. So 144 divided by 342 is 42.1%. All right, so 42.1% carbon in sucrose. So you could figure out the total mass of carbon in an actual Snickers bar. But either way, let's keep moving. All right, so let's calculate the mass percent of each substance in of each of these substances. I have acetylene here, and I got benzene here. So take a moment, pause it up, and try it. And I'll do it on the side here. Okay, so this is 12, 24, 2 times 12. This is 1 times 2 is 2. 2 is 26. Okay, 24 divided by 26 times 100. This thing is almost entirely carbon by mass. 24 divided by 26 is 92.3% carbon. Alright, 92.3% carbon. With this guy. Alright, so it's going to be 12 times 6, okay, and then 1 times 6, 6. 12 times 6 is 72. This thing here also seems to be a lot of carbon. Alright, and then this point we got 78. So percent carbon is 72 divided by 78 times 100. Let's try that out. Okay, so 72 divided by 78 equals 92. Same number. So, in this case, 92.3%. Even though we have different numbers of things. So what are the empirical forms of these guys? What is an empirical form? It's the simplest ratio of atoms. Simplest ratio of atoms. So I could take this guy and convert it to its empirical by dividing it out. So that really, if we analyze this, we'd find 1 carbon for every 1 hydrogen. And here, if we analyze this, we'd find, same again, 1 carbon for every 1 hydrogen. So these are the empirical formulas. So in reality, the ratio of carbon and hydrogen is the same, which is why these are the same. Interesting. Okay. So which of these substances of these 100 gram samples would give you the most mass of carbon? So think about that for a second. A few things you might want to consider here. Let's flip these to empirical formulas first. Which of these is not wasting mass on other things? So each of these has 100 grams. How much of it is the 100 actually in carbon? So this guy is CH2. Now this is benzene. Benzene C6H6. So I'm going to change that to CH. Cyclohexane would be CH2. Glucose would be here, CH2O. And methane is CH4. That is empirical already. So which of these has, now it might be easier to see, which of these guys has the most percent mass carbon? Which of these is wasting none of its mass of carbon on other atoms? And that would be the benzene has the highest percent mass. Alright, and you could calculate it. 12 divided by 13 would be times 100 would be the answer for that guy. So really high. Alright, so now empirical and molecular formulas. So in this case, we're going to use percent mass carbon, which we just solved out. Can you go backwards to find the formulas? And here's sort of the rules which you're going to want to kind of jot down. But number 1, select a sample size. The most common sample size to choose would be 100 grams, because the percentage is based off 100 grams. So this would just be 27.3, 72.7. Convert to moles, because a formula is a ratio of numbers of individuals. Okay, so let's do that. Dot line, get rid of grams, go to moles. 1 mole is 12 grams. And this guy here is get rid of grams, go to moles. 1 mole is 16. Okay, let's do the math for both of these at once. 27.3 divided by 12 is 2.275. 2.275. And this one over here is 72.7 divided by 16 equals 4.54. 4.54. moles. This is moles. Now you might think to yourself, I don't understand why I can choose my own sample size, because if I choose a different sample size, then my moles would be different. Yes, your moles would be different. We chose a 100-gram sample here. If you chose a 10-gram sample per se, 10 grams, how would it be different? It would be 0.227 and 0.454 moles. So the moles themselves would be different, but they would still correlate the same ratio between the two. The reason why they correlate between the two the same is because of the formula. In the formula, you'll find that this substance has carbon and this substance has oxygen. And the numbers of carbons and the numbers of oxygens, these numbers, X and Y, are static. And on average, the masses of these things are static. So if these two things are static, then the ratios of masses will also be static. And the ratio of numbers is static. So here we go. So now you might be able to see I got more particles of oxygen than I do carbon. So this number right here is larger than this number. Alright, so how do we do a better job of seeing this? Well, what we do is we divide by the smallest one. And what that does, it sets this one to 1, 2.275, divided by 2.275, and we're going to get here, this equals 1. So my ratio, all it does is this gives me my empirical ratio. Empirical, because this is 1. And I can't get any smaller than that. 1 to what? Okay, 4.54 divided by 2.275 equals 1.9996, or basically, essentially, 2. Alright. My formula is CO2. Now, this is my empirical formula, mind you. It's the simplest ratio of atoms in the substance. It doesn't mean that the substance has to be CO2. There are other options. So it could be, for example, CO2, C2O4, C3O6. They all have the same empirical formula of CO2. How do I convert an empirical formula to molecular formula? Okay, well, first of all, you need your molecular weight. Okay, the actual one weighs that much. So, don't worry away, that's this guy. So it's the closest one, that's 2. How would we do this? We would take your molecular weight divided by your empirical weight. How much this thing weighs? So this thing is 12 plus 16 times 2 equals 44 grams per mole. So if this was 44, then this would be your actual result as well. So it can be that your empirical formula equals your molecular formula. But I'm going to take the 89.2 divided by the 44, and you're going to get basically 2. That means your empirical formula is doubled times CO2, which gives you C2O4. That is my empirical formula. This thing, if it can have a charge, is referred to as oxalate. Okay, so there's an example. Determine the empirical formula for this guy. Okay, so take a moment, try it on out. So this guy is going to be sample size to 25.9 grams, 74.0 grams. Dot line, get rid of grams and go to moles. Dot line, get rid of grams and go to moles. 1 mole is 14, 1 mole is 16. Take a moment to calculate them out. .85 is my moles of nitrogen. And then the oxygen is 74.0 divided by 16 is 4.62. So we have 4.62 moles. Now, next step, divide by the smallest. 1.85, 1.62. Alright, this is going to be equivalent to 4.62 divided by 1.62 is 2.85. Alright, so in this case, 1.85, that's an issue. Okay. Okay, so alright, so we take 4.62 divided by 1.85 and we get our ratios, 1 versus 1.5, or 2.5. So we have 2.5, okay, 2.5. Now that means we have nitrogen, for every 1 nitrogen, there is 2.5 oxygens. We can't have half an oxygen. So to get us out of this fraction, we're going to multiply both of these guys times the reciprocal of 1/2, which is 2. And that gives us N2O5. And that is our empirical formula. If we were to take the 108, so okay, what's the actual formula? Do this thing, add everything up, and you'll see you get 108 for this thing. And therefore, that these two guys are the same. So the empirical formula, empirical weight equals the molecular weight. So the actual molecular formula is N2O5. Let's add it up just to make sure here. The N2, 14 times 2 equals 28. And the oxygen is 16 times 5. Alright, so 16 times 5 equals 80. And that is what I thought it was. This is 80. Therefore, 108, and that's my answer. You have plenty of opportunities to try some of these out. I have another example on my slide here, which we might do in class, but we've been here long enough. So here's just another example where you can try it out on your own. And we'll stop there for today. Thank you.